Yeah. Good evening, everyone. My voice is audible.
Yes, sir.
Okay. Now we start the session.
Okay, sir.
Okay, sir.
Balu,
Balu,
sir.
sir.
Uh, Suresh, is my voice audible?
Yeah, audible, sir.
Let me try. So yesterday we have seen the module. So I welcome all of you to the day 3 of the 1 month workshop on design of digital circuits using Verilog HDL. So yesterday we have seen the various or the different things how the HDL will be useful, and moreover we have seen how you can represent a module in the Verilog HDL. So now let us see further. Okay, so if you are seeing the Verilog HDL, in the Verilog HDL the same program can be written in different styles. So on the screen you can see a 4 to 1 mux here. Okay, so these 4 to 1 mux, so if you see here it is modeled in the structural style. Okay, so the circuit what is specified here, so it is specified in terms of the instantiations of the low level components. So here the low level components are the logic gates. Okay, so these logic gates are predefined in the Verilog HDL, so they are called as primitives. So by using the predefined Verilog primitives, okay, so we are connecting a 4 by 1 mux. So this type of structuring, is called as structural style. So based on this structural style, so what you do is, so you write the program. So structural style of writing the program is, so the circuit will be specified in terms of the predefined logic gates, which are known as Verilog primitives. So these are defined in the programming language, and their interconnections will be written. Okay, so this is about the structural style of designing. And if you see here, so it is about the data flow style of designing. Okay, so this style is very similar to that of the logical equation. So you can see here, although in general it is not limited.
Sir.
Hello.
Sir, enlarge the screen, sir.
Yes, I have to use. Meanwhile, I have to use the board also. So I am not enlarged. I have not enlarged it.
Okay, sir. Okay, sir.
So if you see here the data flow style here, so what happens? So here you can see the logical and logical and logical and logical and logical not. So these are the various things. So that is various operators what you can see here. So by using the various operators that are inbuilt in the Verilog HDL, so if you design, so if you make the specifications out of the expressions made of the input signals and assign them to the output, so that is called as the data flow here. So this data, in the most cases, so data flow approach is very easy, and it can be easily translated into the required structure, and it can be implemented. So what you can say is that, so data style is similar to that of the logical equations. Okay, so by taking the predefined operators in the Verilog, so what you do is that, so you will create the equations, and by using this data manipulating equation, so we will specify the relation, we will specify how the data is flowing between the inputs and outputs. So it is the data style flow, and the next one is the behavioral style here. So you can see in the behavioral style what it specifies. It specifies the circuit in terms of its expected behavior. Okay, so if you can see here, there are two selection lines. So if selection line is the depends upon the selection line, what happens? You will get the output. So like that it will specify. So if selection lines are these values, so the output will be like this. So like this it will specify the functionality of the outputs. So based on the circuit behavior. So this is known as the behavioral style. Okay. So you can see here, these are the different things. Okay. So first one is structural style. Second one is data flow style, and third one is the behavioral styles. Okay, so these are the three styles of writing the program in the Verilog HDL. So now let us see here. Okay, so let us see how you can write some programs here, some programs for some module declarations for some of the gates. For example, now I want to write a module declaration for AND gate. So module declaration. So first I want to write the module declaration for AND gate. Okay. So what is the syntax? So when you are writing, so the syntax is module. So next module name should be there. Okay. So here you should not use AND. So you should not use AND. Why? Because AND is a keyword. So you can use AND gate or AND 2 if it is a 2 input AND gate. So AND 3 if it is a 3 input AND gate. Or here you can use your name also. But the suggestion is that if you are using the module name, that would specify the function, that would specify the functionality of your design. Okay. So module AND gate. So here what you have to write, here we have to specify the list of port names. Okay. So if you take an AND gate, so 2 input AND gate, this is the 2 input AND gate. We have the inputs as A and B, output as C. Okay. So specify the output as C, and after that specify.
Sir.
Hello.
Sir, teach somewhat slowly, sir. It seems to be quite fast for us.
Okay. So let us see how to write the module. So as we have seen the syntax of the module yesterday. So the module syntax is module name, list of ports. Okay, so first module, after that module name. Okay, you can keep anything in the module name here. So I am taking it as AND gate. Okay, so I am taking it as AND gate. So this module name can be anything. So it should be identifier. Okay, but it should not be a keyword. So here if you use only AND means what happens? So AND becomes a keyword. So therefore you will get the error. Okay, so you can use AND 2 or AND gate. Here you can use your name also. But the problem is if you are using any other thing apart from the functionality of the circuit, so it will not specify to the user who is looking into your code. Okay, so the module name should be written in such a way that it should specify the functionality of your description. Okay, module name. So after that, list of ports. So here what are the ports here? So C is the output port. So here you can write the output ports followed by the input ports, or else you can write the input ports followed by the output ports. Okay. So, but when you are writing for the primitives, so that means for the predefined gates in the Verilog, that should be in such a way that output should be followed by the inputs. As I told you, AND gate is predefined. Okay. So if we are using the predefined AND gate in the Verilog, here we have to specify the output, then followed by the inputs. Okay, for any thing that is predefined in the Verilog HDL, so which are known as primitives, for them we have to specify first the outputs, then followed by the inputs. So in the module declaration, you can specify in the either way. You can specify the outputs followed by the inputs, or inputs followed by the outputs. Okay, so C inputs I have written. So next after that, so out inputs are A comma B. So outputs, inputs. So next we have to specify. Here we know after drawing the circuit, here we know what are the inputs and what are the outputs. Okay, but the code, the software doesn't know what are the inputs and what are the outputs. So therefore we have to specify here. Okay, so input. So input A comma B. So input A comma B. Okay. So these are scalars. So since these are scalars, directly I am writing a comma b. Okay. So if the same width inputs are present, you can specify within the single input. Okay. If there are inputs with multiple widths, means we have to specify them separately. And output C. Okay. So this is the port declaration. So this further follows depending upon the style of writing the program. Okay. So for example, next, if you are writing the program in the AND gate, what happens? So AND gate means, so here we are writing the program in the gate level. So if I am writing the program in the gate level means, so AND is the predefined word in Verilog. So AND, okay. So there next we have to give the instantiation name. Okay. So for this code, so for this AND gate, so I have taken the instantiation name as Z1. Okay. So I'm calling this device as Z1. So G1. It is your wish. So you can keep this instantiation name or you can ignore that. Okay. G1. So AND gate is a primitive, what I am calling. So write first the output, then followed by the inputs. Next, end module. So this is how you write the program for the AND gate here. So it is the gate level description. Okay. So now let us see a small circuit here. Okay. For example, this is the circuit I am taking now. So this is an AND gate. So this is an OR gate. Okay. So here the inputs are A, B, and B is connected here, and this is C here. Okay. So A is connected here, and C is connected here. Okay. So this is the circuit. Okay. So here we have the predefined gates. Okay. So it is the AND gate. For this we have to write the program. So if you want to write program for this, so you can write the program in any of the descriptions. So in the structural description you can write, in the behavioral model you can write, so in the data flow model you can. But in order to write the data flow program for this circuit, so you need the equations. So in order to know the functionality of this circuit, in order to write the program in the behavioral model, you require to know the exact functionality of this circuit in terms of a truth table, or you should know the equations. Okay. So in order to know the functionality of this, so as we doesn't know, so in order to generate the functionality for this circuit, again we have to go for the writing up of Boolean expressions. After that, again we have to reduce the redundancy terms, and at last you get the required functionality. So it takes time here. So in order to overcome that, so what you can do is that directly you can write the program in the structural design. Okay. So now if you see, this is the AND gate. So this is the OR gate. So this is the XOR gate. So this is the AND gate, and this is the OR gate. Okay. So in the Verilog HDL, so we have predefined gates. Okay. So where AND gate is predefined as AND, OR gate is predefined as OR, XOR gate is predefined as XOR, XNOR gate is predefined as XNOR. Okay. So these are the predefined names. So next, NAND gate is predefined as NAND. Okay. Next, NOR gate is predefined as NOR. So NOT gate or inverter is predefined as NOT. So these are the predefined names in the Verilog for the logic gates. So these are known as the primitives. Okay. How you can declare a primitive means, so AND gate primitive, how you can declare. Okay. First is the gate name. So after the gate name, next we have to go for the instantiation name. gate name, instantiation name. After that, list of port names. So these are the list of port names. So in the list of port names, what you should see is that since these are predefined primitives, first you should write the outputs, then followed by the inputs. In case of module, you can follow the either way, but for the predefined gates, you remember that. So first we have to write the outputs followed by the inputs. Now let us see how you can write the Verilog program for this gate here. Okay. Yeah. So first we have to give the names for this AND gate. So I am calling this AND gate as G1. Okay. So since there are many gates in the circuit, so what you can do is that, so you can name the gates. Okay. You can name the gates for our understanding. Okay. So G1, I am calling it as G2. So I am calling this gate as G3. I am calling this gate as G4. I am calling this gate as G5. Okay. So first write. So logic circuit. So model name is logic circuit. Okay. So in the module you can write your wish. So outputs followed by inputs or inputs followed by outputs. Okay. So output is Y. Inputs are A comma B comma C. Okay. The output is Y. The input is A Y. Inputs are y, A comma B comma C here. Okay. Next, we have to specify the inputs and outputs separately. Now specify it. Input. So here we have three inputs. The inputs are A, B, C, and these inputs A, B, C are scalar. Okay. So these are scalar inputs. So therefore you can write them together, A comma B comma C, input A comma B comma C, or else you can write separately also, input A, input B, input C. You can write separately or you can write together. Okay. So when we can write the inputs together means when the size of the inputs is same. So here A, B, C, the three inputs are of scalar. So therefore input A, B, C. Next, output Y. So output Y. Okay. Next, here there is a term here. So the connection between two gates is known as wire. Okay. So actually in case of VHDL it is termed as signal, but here it is termed as wires. Okay. So the connection between two different gates is termed as wires here. Okay. So here from this G1 to G5 there is a wire connection. So name this wire connection as W1. Okay. Next, the connection between G2 to G4 is termed as W2. It is wire 2. So there is a connection in between the output of G3 to G4. So let it be wire 3. Okay. So there is a connection in between G4 to G5. So let it W5. So W4 you can take. So W4. Okay. Now start from the first gate. What is the first gate here? AND gate. Okay. So AND gate is the first gate. And the primitive is AND. Okay. So AND gate and its declaration will be AND followed by the label name G1. So this label name or instantiation name is not must. So it is optional. So it is your wish. So you can keep the name or you can ignore that. Okay. So G1 followed by G1 followed by next one is what is the output of this gate here. Okay, so the output of this gate is nothing but the wire 1. So whatever the output we are connecting from this gate to this input, so that thing we have named as W1. So therefore the output of the gate is W1. The output of the gate is W1 followed by the inputs. So what are the inputs to this gate G1? A comma B are the inputs. So write the inputs A comma B. Next, G2. So G2 is a OR gate. So OR gate is predefined as R. Okay, R. G2 is the label name of this gate. Okay. Then what is the output of OR gate here? The output of OR gate is taken as W2. Okay. The output of OR gate is taken as W2. So what are the inputs to the OR gate here? The inputs to
C
the
and
OR
B.
so are nothing but A and B. So write the inputs.
Sir, C and B, sir, inputs for OR gate.
Yeah. I have written.
Sir, you have written A and B, sir. Inputs are C and B.
Okay. Sorry. C and B. So next gate is XR gate. So which is predefined as XR. Okay. So XR gate is predefined as XR, and the instantiation name for this XR gate is G3. Okay. So what are the inputs for this? Output for this is W3. So the inputs are A comma C. So the inputs are A comma C. Okay. So next after that, okay. So what is the next gate here? So the next gate here is G4. So G4 is again AND gate. So AND gate can be taken as AND. Okay. AND gate primitive name is AND, followed by the instantiation name, which is known as G4. So what are the output? What is the output of the G4? W4 is the output of the G4. W4 is the output of the G4. So what are the inputs to this G4? W2 and W3. So the inputs to this G4 are W2 and W3. Okay. Next. After this, next gate is OR gate here. So OR gate, whose instantiation name is R and its name is G5. The output of the OR gate is Y, and the inputs are W1 comma W4. Okay. So here we have specified W1, W2, W3, W4, but so we have to specify them. So these are called as whites. So therefore, white. So in order to specify these signals here, so these are termed as whites in Verilog. So after declaration of input and output, so specify them. White. Okay. So here whites are W1 comma W2 comma W3 comma W4. Okay. So next R G5 is finished, and next one is, so we have specified everything here. So therefore write end module. Okay, so you can write the end module. So this is the structural or gate level description. So this is the structural or gate level description of your circuit, which we have seen on the screen here. Okay, so like this you can write for any architecture. Okay. Now if you can see here, the every line here is terminated by a semicolon, but the end module is not terminated by a semicolon. So we should not terminate the end module line by using semicolon. And also remember that, so there should not be a space between end and module. And one more thing is that, so whatever the things you are writing here, so everything should be in the lowercase letters. So that we have to remember. The first thing you should remember is that whatever the things you are writing, so these should be the lowercase letters. And second one is, apart from the end module, so every line must be terminated by a semicolon. And when you are writing the end module, there should not be any space between the end and module. So these three are the thumb rules. So many people will be doing the mistakes here. Okay. Next, let us see how module declaration we have seen here. So now let us see how you can instantiate the module. So how you can instantiate a module. So a module instantiation. So module instantiation. So module declarations are the templates from which designer can create actual objects. So modules can be instantiated inside the other modules. For example, I have created a module here. Okay, so I have created a full adder module. That full adder I have to use in the ripple carry adder. So that means the full adder module which I have created, I can use that module for the ripple carry adder module. So here what we have to do is we have to instantiate, or we have to call the full adder module to use in the ripple carry adder. So let us see the syntax for the instantiation names here. Okay, so in the module the same thing, module name, or else directly what you can write here. So module name, so module name, instance name underscore one, port list connections. Okay, so it is the post list connections. Okay, so like this you can use it. Okay, so next module name, instantiation to post list connection. So like this we can instantiate any number of modules within the other modules. Okay, so let us see how you can use that. Okay, so for example, now we want to design a 4-bit triple carry adder. So I want to design a 4-bit triple carry adder. So a 4-bit triple carry adder is a 4-bit adder here. So where the carry of the previous stage will be rippled to the next stage. Okay, so let us first, so in order to go for the gate level or the circuit level description, so you need the circuit compulsorily. Okay, so first you take a ripple carry 4-bit triple carry adder here. So 4-bit triple carry adder. Okay, so here the inputs are A0, B0, A1, B1, so A2, B2, and A3, B3. So these are the inputs here. So why? Because two inputs A and B with 4 bits each. So A0, B0 is given to one full adder. Why? Because when you are adding here, so we have to add like this: A3, A2, A1, A0, B3, B2, B1, B0. So first you have to add the 2 bits A0, B0, and you get the sum C0. So whatever, there will be an input carry here. So if you will add this, in order to add these 3 bits, you need a full adder. So after adding this, the resultant will be the sum, and also we get a carry. So this carry will be forwarded to the next stage, okay, which is C0. So if you add A1, B1, and C0, you get the sum S1, and whatever the carry we get here, C1, so that will be taken to the next stage. Again, you can add A2, B2, and C1, you get the sum S2. So the carry is C2, which will be repeated to the next stage. Okay, if you add here, you get sum S3, and the carry is what you get is the final carry here. Okay, so since at each and every stage we have to add the 3 bits here, so you require a full adder here. Okay, so full adder, so take 4 full adders. So for the first full adder, we have to give the inputs A0, B0, and C0. Sorry, Cin. So what is the output you get? Sum S0 is the output, and also you get one more output C0, which will be given as the input to the next stage. Okay, so take it be as C0. Okay, next. So the second full adder A1, B1, and C0 will be added. Okay, so the output will be S1. So the output will be S1 here. And next, what happens? The C1 output, carry output will be given to the next full adder. You get the sum S2. So after this, you will be again getting the C2, the output carry, which will be given to the next stage, and the sum is S3, and also you get is the final carry as C out. Okay, so it is the 4-bit triple carry adder, so which consists of 4 full adders. Okay, so here there is a module known as full adder. Okay, so we have to this full adder module is specified in some other module. Okay, so we have to instantiate that. Okay, so we have to instantiate that. So here what you can do is that first define the port names here. So how you can define the port names? The first thing is module. So ripple carry adder 4. So why I have taken RCA 4? So now it specifies that it is a ripple carry adder of 4-bit. Okay. So module name. So first write the outputs. Okay. So here you can write the outputs in 2 types. Okay, so you can specify S0, S1, S2, S3 separately, or you can specify them as the required vector form also. So what I will do here, so I will specify them in the required vector form here. Okay, so I take the output as yes, so that is the sum is the output, and one more output I will get. So you here C0, C1, C2 are not the final outputs. Only sum, that is S0, S1, S2, S3 bits and Cout bits are the final outputs. Okay. So, but we are not bothered about C0, C1 and C2 here. Okay. So here sum is the final output and Cout is the final output. Okay, carry out. So after specifying that, next declare the inputs. So here inputs are A comma B. Okay, and one more input is C in. Okay, so first I have specified the outputs. So after that I have specified the inputs. So next I have to specify what are the inputs and what are the outputs separately here. Okay, so output. So here the sum output has 4 bits. So therefore I can specify it as 3 down to 0. Yes. Okay, this is how I can specify a vectored output or input. So 3 down to 0 means, so the bits will be assigned as S3, S2, S1 and S0. So whatever the data you are giving 1011 for suppose. So the first will be S3, second will be S2, third will be S1 and this will be S0. So like this it will assign. Suppose if you assign like this 0 to 3 means, so what it will do is S0, S1, S2, S3. In the either way we can assign here. So if you are assigning 3 down to 0 means we have to assign in all the cases in the same way. Okay, if you are assigning 0 to 3 means we have to assign in all the cases in the same way. So you should not mix the assignments here. Okay, so 3 down to 0 sum. So again output Cout. So here I have written the sum and carry output separately. So why I have written the sum and carry output separately means, okay, sum is an output whose size is 4 and Cout is the carry out is output whose size is 1. So therefore the sizes are different. So therefore I have specified the outputs differently. And next one is I have to specify the inputs here. Okay, input. So here I have 3 inputs A, B and C in. The inputs A, B is of 4 bits. So therefore input 3 down to 0 A comma B. So this specifies that, so in A, B are inputs whose size is 3 down to 0. Okay, next input C in. So input C in means what happens is input C in means, so C in carry input is having only 1 bit, that is scalar. So we are specifying it separately as C input. So now are there any wires here? Yes, we have wires here. So what are that wire connections? So which connects two different components is nothing but a wire here. Okay. So C0 is one wire, okay, C1 and C2. So specify that wire C0, comma C1, comma C2. Okay. So I have specified wire C0, comma C1, comma C2. Now So if it is a gate means directly. So normally what happened in the previous case, since we have used the gate here, so directly we have written the gate name. Okay. So now these are the full adders. So therefore, give the module name of this full adder. Okay. So what is the syntax which we have seen? First we have to write the module name here. So what is the module name of this full adder? I have taken as FA. So the module name of the full adder is defined as FA, that we have to define. So it is not predefined. So all of you make sure that this module full adder should be written by us only. Okay. So when you are writing the full adder program, we have to specify the module name as FA. Okay. So whatever the module name here we are using, so that module name we have to specify when you are writing the program for the full adder. Okay. Full adder. So after that, instantiation name. So let I am taking this as L1, L2, L3, L4. So L1, L2, L3, L4. Okay. L1, L2, L3, L4. So the instantiation name. So I am taking the instantiation name as L1. Okay. Then followed by the port connections. Okay. So then followed by the port connections. So from where you can come. So from here. So let the port connections here in the module you have given some cout like this. So name them in the same order. So what is the output of first full adder? Output of first full adder is?
Sir, yes, not.
Yes, not. Okay. So yes, in brackets we have to keep 0. Why? Because so since it's a vector, we have to specify S of 0 means that is the S0 bit here. Okay. So next, what happens here? So next.
Sir, we are writing module instantaneous now, right?
Yes, yes.
Okay. Sir, module instantaneous means we have to describe the what the operation is going on in the circuit.
Yeah, so for the whatever the circuit is given on the circuit is given here, so based on that we have to write here. Okay, so here in the previous case what you have done, so in the circuit these are the logic gates. For example, if we are the logic gates means you can directly write the predefined gate names here, but these are the full adders. Okay, so these full adders are not predefined in the Verilog, so we have to write the program separately for the full adder. Okay, so therefore the program name of the full adder or the module name I am taking it as FA. So FA followed by the label name, then followed by the first sum output. Then what is the carry output for this? The carry output for this is C0. Okay, the carry output for this is C0, which I have taken as the wire. And next, what are the inputs? The inputs will be A of 0, comma, B of 0, comma, and the input is carry input is C in. Okay, carry input is C in. So end with semicolon. So next, come to next full adder. So FA. Okay, what is the label name? The label name is L2 here. Okay, the label name is L2 here. So what is the sum output here? The sum output is S of 1. Okay, so what is the carry output here? The carry output is C1. The carry output is C1. And what are the A and B inputs? So A and B inputs are A of 1, B of 1. And what is the carry input? The carry input for the second full adder is C0. Okay, is C0. Next. So next, for the next full adder. So full adder label name is L3, and it is S of the sum is S of 2, comma, carry is output is C2, and the inputs are A of 2, comma, B of 2. So A of 2, comma, B of 2, and the carry input for this is C1. Next, last full adder FA. So label name as L4. Okay. The output is S of 3, comma. So what is the carry output is C out. Okay, C out is the carry output. The inputs are A of 3, comma, B of 3, comma. So A of 3, comma, B of 3, comma. So the input is carry input is C2. Okay, carry input is C2. So now we have described all the blocks present in the circuit as well as their interconnections. Therefore, write it as end module. So write it as end module. So now I am writing it as end module here. So this is how you can specify a given architecture by using the module and module instantiation. So this is also referred to as structural style of designing the program here. Okay, but one thing what you should understand here is that, so here we have used the full adder as FA. Here we know the designer knows, because he has written the program, the designer knows that, so the full FA is nothing but the full adder, but the computer or the software by which you are simulating, so the software doesn't know what is meant by FA. Okay, so you just take FA as an identifier. So you have to specify the functionality of this FA also. So how you have to specify? We have to specify by taking the module. So module FA. So in this module FA, we have to write the program for the full adder here. This program for the full adder can be based on any style of programming. So you can simply follow the structural style, or you can follow the data flow style, or you can follow the behavioral style. Okay, so one thing we have to remember is that, so this module name, full adder module name, should be the FA. It should be the same name what you have used here. Okay, so if these two are different, means automatically these two again becomes a separate programs, so they will not be instantiated with each other. So this will again be a separate program here. Okay, so this is about the writing of the module instantiations here. This how you can write the module instantiation programs. So I think all of you have understood that. So is it okay about the programs what I have shown you?
Yes, sir. Yes, sir.
Yeah. So
I understood,
yeah.
sir.
So let us see the remaining styles. So after this, we can go again in depth here. So in the presentation, we are talking about the MUX 4x1 multiplexer. Okay. So it is the 4x1 multiplexer. How you can write the Verilog code in the structural style here. Okay. So here the inputs. So the inputs, first one is module. Okay, module 4_2_1. Okay, so it is a valid identifier. Okay, so module name. After that, first we have to specify the outputs. So what is the output here? Out is the output. So next, what are the inputs? In 0, in 1, in 2, in 3, the 4 inputs. Okay, and after that they have specified the selection line. So selection 1 comma selection line 1 comma selection line 0. Okay, so after specifying the inputs, again we have to specify what type of codes they are. Output out, then followed by the inputs here. So input in 0, in 1, in 2, in 3, and selection line 0 and selection line 1. So these are the single bit inputs. Okay, so after this, so here there are whites here. Okay, so what are that whites? The output of, so the output of 2 NOT gates, we get 2 whites. So here they specified these whites as not select 0, not select 1. The output of first NOT gate has not select 0 and not select 1. And so they have specified the outputs of AND gates as Y0, Y1, Y2, and Y3. So they have specified this whites. Okay, so after specifying the whites, so next come from the so here you see means, so here they have not taken the instantiation name. As I told you, instantiation names are optional. So first they have taken the NOT gate, this gate. So NOT. So the output of the output of this NOT gate. Okay. So why we have specifying the output here first means, so these are the primitives. Since these are primitives, we have to set the output, then followed by the inputs. So NOT output of this gate is not select of 1 0. So this gate they have taken. Okay, and input is selection 0. So next for this gate, so not selection 1 is the output, selection line 1. Okay, so for this first AND gate here, the output of this first AND gate is Y naught. So the what are the inputs for this AND gate? In 0 is one of the input, so in 0, and one more input here is selection not select 1. So not select 1, and one more input is not select 0, not select 0. So like this, so they have specified all the AND gates and OR gates. So after specifying the internal connections of all the AND gates and OR gates, so they have written the end module. So this is the structural style. And coming to the data flow style here, so what they have taken, so first as usual they have specified the module and the module name and the inputs and outputs. After that, so they have specified, so in order when you are writing the program in the data flow here, so we have to use the statement known as assign. Okay, so assign out. So we are assigning the output variable to this equation. Okay, so what is this equation here? Here there is logical AND. Okay, so logical AND of this. So this is the logical NOT. So for this first AND gate here, what you are giving the inputs as in 0. So in 0, one more input is it is a NOT gate here. The output of this NOT gate is not selection 1 0. So NOT gate here we have used it. So here just NOT gates, the symbols of that NOT gates. So basic on this operators symbol, so they have specified the circuit here. Okay, and the next one is behavioral modeling. So in the behavioral modeling, what they have after specifying the inputs and outputs, so they have used the sentence known as always. Okay, so this we can see later in depth. So here what they have done, so they have taken the behavior of this multiplexer. The selection lines of the multiplexer are 0 0. If the selection lines of the multiplexer are 0 0 means, so the output will be connected to the input 0. So output will be connected to the input 0. If the selection lines are 0 1, the output will be connected to the in 1. If the selection lines are 1 0, the output is connected to the input 3. If the selection lines are 1 1, the output is connected to the in 4. So like this, here we will specify the functionality of your multiplexer. So I think now you have understood how you are writing the program in the three different structures. Okay, so this is how to write a same program by using the different styles. Okay, so after this, let us see the lexical tokens in Verilog HDL. Okay, so what are lexical tokens? So lexical tokens are nothing but the like the grammar what you have in any language. Okay, so lexical token means, so constitutes the grammar. Okay, it is the grammar that we have to follow in Verilog HDL. So the main important things in Verilog HDL are white spaces, comments, numbers, identifiers, Verilog keywords, and Verilog operators. So these are the important lexical tokens here. So what are white spaces? So white spaces are nothing but, okay, so white spaces are nothing but blank. These are the white spaces. Okay, so let me tell you what are white spaces. So white spaces are /B. So which will, if you use the /B means you will get the blank cursor. Okay, so next /N. So /N means when you use the /N means so the cursor will be pointing to the next line. slash tab if you means, so cursor will give a one tab space. Okay, so these are the white space characters that are used in the Verilog language. Okay, so in any description, the importance of the white space characters is to improve the readability. So by using these white space characters, we can improve the readability in the Verilog programming language. Okay, functionally, they are used to separate uh, different characters for the purpose of readability. Okay, so this is about the white space characters, and the next one. So the next important one is here comments. Okay, so yesterday we have seen the comments. There are two types of comments. One is with the backslash, so it is a single line comment. So double line comment means slash star. Okay, sorry. So you can take this. Okay, slash star. After writing the program again, slash star slash. Okay. So why comments are used? Okay. Why comments are used means in order to make sure for the users to understand what the program is written. So for example here, after writing the Verilog program, in order to understand the functionality of the program means, so we have to go through the total entire program. Okay, so in order to overcome that, you can use the comments for the program. So in this comments, you can specify what you are writing the program for. Okay, and moreover, why we are used comments means, so in order to increase the readability. Okay, so whenever we are writing the program, at some points, if you want to directly narrate the logic to the other persons without going into it, so you can use the comments here. Okay, so there are single line comments and double line comments. So single line comment means whatever the code lines are there, that should be written in a single line. Okay, so if the multiple comments, if you want to specify means, so we can use the multiple comments. So for example here, A is input. Okay, so this is a comment, and this will not be read by the compiler during the syntax check or execution of the program. Okay, so now if you are writing A is input, B is input, so here the comment is not specified. So during the execution of the Verilog program, so this shows as the error, syntax error. Why? Because so there is no comment line here, and therefore the compiler will check it. Okay, so since there are two lines here, we can use the two single lines, like single line comments like this, or else what you can do is that, so you can use the multi-line comment. So A is input, and again B is input. So like this, you can use the multi-line comment. Okay, so this is how you can specify the comments. And the next important thing are numbers. Okay, so in any language, number system is very important here. So in the Verilog, we can represent the integers and we can integer constants, and we can represent the real constants. So which we will see tomorrow, how you can represent the integer constants and how you can represent the real number constants. So after that, the next one is the identifiers. So identifier means, identifiers are the user defined words that are used to specify the function, names of the functions, names of the variables, names of the modules, and various other blocks. Okay, so these identifiers can begin with either a underscore or a letter, but it should not begin with a number. Okay, so normally identifier includes alphabets, digits, and underscore. Okay, and moreover, the identifiers in Verilog are case sensitive. The next thing is Verilog keywords. Like in any other language, in Verilog HDL also, there are special words. So the meaning of these words are reserved. So these are known as keywords. For example, and is a keyword, so which specifies that and operation should be performed. So like this, there are different keywords in Verilog which has the specific meaning. So the next one is operators. Okay, so in order to do the arithmetic and logical manipulations, the Verilog HDL is provided with different operators. Okay, so there are arithmetic operators, logical operators, shift operators, replication operators, conditional operators. Okay, so there are different types of operators, reduction operators. There are different types of operators available in the Verilog HDL. So by using these Verilog operators, we can able to write the data flow modeling very easily. So this we will be see in detail in the further classes. So these are the lexical tokens that we come across in the Verilog HDL. Okay. So I hand over to Suresh for further
Sir?
things. Hello.
Sir,
Please tell me.
sir, can we get this textbook of this Verilog HDL, sir?
Yeah, you can.
Can
There
you?
are number of textbooks in the websites or in the net, so you can directly Google it. So digital design Verilog means you can get a number of textbooks. You can
Sir,
download.
which one you prefer, sir? Which is the best?
So normally for the academics, most of the universities will be using the digital design through Verilog HDL by Padmanabham.
Okay.
So that is the textbook most of the universities will be using. So apart from this, there are number of books. Okay, so Verilog Primer by Bhaskar. So J Bhaskar, it is also one of the good book. Okay, so there are many books. So depending upon the syllabus or depending upon the thing what we want to learn, so there will be a lot of variation. So these are the two basic books. Okay, digital design through Verilog by Padmanabham, and one more is Verilog Primer by Bhaskar. Okay, these two are the basic books. So by using these two books, you can learn the basics of Verilog easily.
Okay, thank you, sir. Sir, can you send me the PDF or any PDF, the book that you
Yeah,
have?
I will send. We will send, but it takes time. So during this course, uh, duration of this course, we will send it. So no issues about it.
Okay, sir. Okay. Thank you so much, sir.
Yeah, okay, sir. Yeah, like we definitely send it the materials. Okay.
Okay, sir. Okay. Thank you, sir.
Okay, thank you. Okay, is there any more questions? Yeah, is there any more questions? Okay, sir. Okay, Bala sir, now we close the session, sir.